So here's what we're going to do today. We're going to talk more about signals, about filtering and making filters. And I'm just going to start by double checking to see how much everybody's comfortable with in terms of their filter knowledge. And then we'll do some practical applications. So there's going to be a decent amount of MATLAB. There is. Okay, so your generic filter looks like this. So we think about, this is a transfer function. And what you'll notice about the transfer function is got sort of like three main elements. Again, this is all stuff you may have seen before. So the first thing is it's got zeros. Okay, so zeros are values of S that make, that set the numerator to 0. Okay, and when you express your transfer function factored like that, it works out very nicely, doesn't it? Like, you just read them right off. You've got a 0 at negative z1, a 0 at negative z2. Like, you're good to go. And then likewise, you've got your poles are values of S that set denominator to 0. And then you've got a gain. So in terms of plotting the magnitude response, what does a pole do for you to your magnitude response? Right. Poles reduce the slope, and I'll do an example. They reduce slope by 20 dB per decade, and zeros increase the slope by 20 dB per decade. All right? So if I come to you, for example, and I say, I've got a filter that's h of s equals S plus 100, S plus 10,000. Okay, so what do I have going on here? How many zeros, how many poles?
2 zeros.
Actually, I don't do. Is that what I want? You know what? I'd like to put this one in the denominator, actually. Can I do that without ruining your notes? Is this S plus 100 or S minus 100?
S plus 100.
What would happen if it was S minus 100? Where would my pole be? Where's my pole right now? Negative 100. Do I want my pole to be at negative 100 or positive 100? Negative. You always want your poles to have negative real parts so that the system is stable. Good. So I've got 1 0 and 2 poles. Where's the first one of them? What comes first, the 0 or one of the poles?
The 0.
Yeah, where is my 0? I have a 0 at omega equals 0. Okay, so where is that on this graph?
At the origin, infinite distance to the left.
I'll give you a hint. This is a log scale. Okay, so let's say this is 1. And this is, let's say 100. Okay, let's say that's 100. No, 1,000. Let's say that's 10,000. Okay, so this would be 100. Sorry, if that's 10,000 and this is 1,000 on my log scale, what's this number going to be? 100, right? The whole thing about a log scale like on a regular scale, a linear scale, equally spaced points, like you add the same number to get from one point to another. On a log scale, you multiply by the same number. So here, between every hash mark to the left, I divide by 10. So there's 100, 10, 1, 0.1. How far back do I need to go to hit 0? All the way to the phone, okay? To infinity, right? So that's the thing. Where do I draw my... So where is this pole at s equals 0? All the way back at negative infinity. So the way I interpret that is I'm going to start... My slope is going to start out at a slope of positive 20 decibels per decade. Yes, sir?
Why does slope start as positive? Since you have 0 at top, that's why.
That's right. That's exactly why. Because remember, every 0 adds 20 decibels per decade to your slope. Okay, so I have a 0, and look, here it is. It added 20 decibels per decade to my slope. It's just that it started adding it all the way over at negative infinity,
So
as opposed to at a specific frequency.
you can't have a negative slope then. No way.
Oh, sure you
Starts at 0.
Well, you can if you had an s in the denominator. If I'd have started it, if I'd have given you this instead, then totally you could have. Right? Then it would have gone down. And I could even build you that filter. Okay? Good. So what's the next thing that's going to happen?
I got a question.
Yes, sir.
You can't identify specifically where it crosses.
Sure, because it's sort of arbitrary where I put the axis, isn't it? Right? I mean, does this y-axis cross at 1 or at 10, or it's arbitrary?
If
Wait.
there was a number in front of us, you could determine where.
No. Well, what we're going to do is, once we're done drawing the shape, we'll label some points so that we at least have a frame of reference. I think that'll help. But we'll do that last. Okay, so what's the next thing that happened? I passed my pole at my 0 at 0. The next thing I'm going to get to is my pole at 100. So what's going to happen when I get to my pole at 100? It's going to decrease my slope by 20 decibels per decade. So if my slope was at 20, and I decrease it by 20, now it'll be at a slope of 0. That's also the same as being flat, right? Okay, so now it's going to be flat. So that's decreasing my slope. It was at plus 20. I decreased it by 20. Now it's at 0. And then I'm going to get to 10,000. And then what's going to happen? It's going to decrease by 20 again. And then that's it. That goes off to infinity. So what kind of filter do I have? Got me a bandpass. Sweet. Okay, now, what's my gain in the passband here? Do I have a good gain, a bad gain? Let's say I want a gain of 1 in the passband. Is that what I have? How can I figure that out without doing any more work than humanly necessary?
Take the high number and divide by the low number. Not,
Sort of. No, I mean, you're on the right track. So here's what we're going to do. We're going to plug in a number. Okay? So let's plug in 1,000 because it's right in the middle. Okay? And we're going to do some engineering ninja sleight of hand so that we don't have to do any more work than necessary. Okay? So, at 1,000, so at omega equals 1,000, let's get the magnitude of this expression. So magnitude of h of omega equals 1,000. Okay, well, you put 1,000 in the numerator, you should get 1,000. So that's easy. Now, let's look in the denominator. You're going to have j 1,000 plus 100. Right? Because s is j omega and omega is 1,000. So I've got 100 plus 1,000j. Now, if I'm truly calculating the magnitude of that, then I've got to take the real part squared and the imaginary part squared, and I've got to add them and then take the square root. But here's what I think is going to happen. Basically, when you factor your expression like this, what happens is you look at this and you say, look, one of these two terms is going to win. If I'm below the pole, or the 0, like if s is smaller than 100, I'm basically going to say 100 wins. 100 is bigger than s. And if s is bigger than 100, I'm going to say forget about the 100. The 100 wins. Okay? So in my case, is S bigger than 100 or less? Obviously, it's bigger. So when taking the magnitude of that expression, I'm going to say forget about the 100. The 1,000 is going to win. Now, is that accurate? Let's find out. Let's do some scratch paper. We'll just do it this one time. The true term would have been, so we have what, 100 plus 1,000j, and I wanted to take its magnitude. So that would be the square root of 100 squared plus 1,000 squared. Somebody want to tell me what that comes out to?
I got 1,004.
1,004.
1,005.
Okay, whatever. So, is it worth doing all that math to get like that one part in 1,000? Not really, okay? So I'll settle for my 1,000 here. Okay, good. Now I come here and I sub in my, again, s equals 1,000. Who's going to win, the 1,000 or the 10,000? The 10,000, okay? So times 10,000. Okay, again, I'm certainly welcome to do the calculation. It's just a lot of work and doesn't get me anywhere. Okay, so what is my gain in the passband? 1 over 10,000. Boo! That's not very good, right? That's 1 over 10 to the 4. That's 10 to the minus 4. How many dBs is that? Remember, every time you multiply by 10, that adds 20 decibels. Okay, so a gain of 1 is 0 dB. A gain of 0.1 is? No. Gain of 0.1. Let's do it. Let's step by step. Right. Right. A gain of 1 gives you 0 dB. A gain of 0.1 is negative 20. A gain of 0.01 is negative 40. And I've got to go, so that's 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4. So as it stands right now, this is at negative 80 dB. Some filter. Okay? So how do we fix that? Let's say I want 0 dB in the passband. Yeah. Problem solved. Just gain. All right, you put a 10 to the 4th there. That erases that 80 dB. Now we're at 0 dB. And hopefully that answers your question a little bit about the zero crossing. Like there's no zero crossing. You just have to label a point. All right, so we can get sort of arbitrarily good at manipulating these, but at the end of the day, it's just kind of like a party trick. There's one more piece of the puzzle that's a little bit more complicated, and that is in the setup I've given you here, I've only allowed for real poles. Have I not? Right. So it's also possible to get terms that I like to write them like this, and I mean, I'm not at all planning on getting into this, although you may have seen this in circuits too. You can also have quadratics in here that when you factor them get you S is a pair of complex conjugate poles. Okay, and those basically work. That gives you sort of a cutoff frequency at omega naught, whatever that winds up being for that expression. And we're going to do an example of that shortly. So the question then becomes, how do you actually design a filter? Like, this is how the math works, and I mean, we could do this all day, but really a more interesting question is practically, how do you build this? And that's really what I wanted to work on today, because that's a computer tool that you need to do that. All right, so am I good? Can I bring the screen down? So what do complex poles do for me? They're kind of interesting. Yes, sir. Yeah, I picked something in the passband because I wanted to make sure that I evaluated what the gain was in the passband. Well, the 100 and the 10,000 are at the cutoff frequency, so they're not a good representative of what's going on in the passband. But in theory, putting any number in the passband would have worked. Oh, look at this. I forgot to plug it in. No wonder you can't see what I'm seeing. All right, let's try that again. Yes?
So now we're going to build a filter like Echo, the capacitor, resistor, and...
No. No, now we're going to actually design. First, we have to pick where to put the poles. Then you can figure out a circuit to actually build them. And I can show you the circuit if you want. But first, we have to go through this exercise of actually planning where to put the poles, because that's kind of a big thing. All right, there we go. Did it resize the way I like? I think so. Okay, clear. Okay, so this will all go online shortly. So we're going to do a little exercise. Oops. All right. So let's bind those, and we'll pop that out. And then I think, what should we put them side by side? Except I want this one on the left and this one on the right, because I'm picky. Okay, so here's what I've done. We have a simple exercise, and that is to build a low-pass filter with a cutoff frequency of 100 hertz. Okay, that's all we're trying to do. Low-pass filter, 2 poles, cutoff frequency at 100 hertz. So look at the plot on the left. I've got 4 filters. Okay, blue, red, green, and pink. Now, do all 4 of those meet my criteria of being a 2-pole low-pass filter with a cutoff frequency at 100 hertz? So let's discuss the 2-pole nonsense. How do I know if it's a 2-pole filter? It's got to roll off at 40 decibels per decade. So let's forget about the pink one for a second. We'll get back to the pink one in just a moment. But let's just start by looking at the other 3. Well, the other 3, these slopes are parallel. Those lines are parallel. And when they're parallel, we know they have the same slope. So if I measure the slope of one of them, I know they're all going to be the same. So let's see here. Let's look at the blue one. What's an easy one to look at? The blue one? Oh, maybe the red one. Okay. So the red one, down here, at a frequency of 10 to the 4th, it's at, can you read that? Negative 80 decibels. You see that? So let's now go back 1 decade. What does it mean to go back 1 decade? Divide by 10. So if I go back a decade from 10 to the 4th, I go to 10 to the 3. All right, now let's see what the gain is at 10 to the 3 on the red one. Minus 40. So in 1 decade, how many decibels did it drop? 40 decibels per decade. It's a 2-pole filter. So what I have here for you is 4 2-pole filters. And look at this. They all have the same cutoff frequency. If I zoom in the pass band, they all pass through. Remember we said the cutoff frequency is where it goes through negative 3 decibels? And look at this. All 4 of them go right through 100 hertz at negative 3 decibels. So we've built all 3 to spec, all 4 to spec. And yet they're very different filters. So let's ignore for a second the green one and the purple one. In fact, maybe I can delete them and see if we have that technology. Oh, yeah. So let's just look at the red one and the blue one. Which is a better filter?
The red.
Why would one be better than the other?
It's got a flatter band pass, or pass band rather.
So there are 2 differences. One is if you look in the pass band, you can see that the red one, oh, come on back. the red one is flatter. What does that mean, to be flatter in the passband? Is that good?
Yes, it's closer to ideal.
Right. Essentially, it's doing a better job of passing the pass frequencies. Right? Because the frequencies that you pass, in theory, you want to pass them all with 0 dB, right? Exactly the same as they went in. And it looks like the red one, for the most part, is doing a better job than the blue one. Still not perfect, but it's definitely doing a better job than the blue one. Now, let's look at the stop band. Who's kicking more butt in the stop band? The red one, okay? So, for example, what do I mean by that? Let's look at 1,000 hertz. At 1,000 hertz, the red signal is giving you 40 dB of rejection, negative 40 dB. That's dividing by 100. Okay, whereas the blue one is only giving you maybe like negative 34 dB. Okay, so there's a difference of 6 dB, which is a factor of 2. Okay, so the red one is actually giving you double the rejection at that frequency than the blue one is. And both of them have 2 poles, meaning that in terms of circuit complexity, right, implementation complexity, they're identical, right? It's just as hard to build the red one as the blue one.
Would 2 poles mean that there's 2 energy storing devices in that circuit?
Yes, it would. 2 energy storing devices. So, can you think of any reason why the blue one would be preferable to the red one? Neither can I. Okay, good. So, let's direct our attention now to the pole 0 maps on the right. So, what you can see here is for the blue filter, what I've done is I've put 2 poles. I've got 2 poles at 1,000 hertz. 1,000? Actually, maybe that's in rads per second. Yeah, I think that's in rads per second, maybe. Okay, so if it's in rads per second, shouldn't it say rads per second? Okay, I'm not going to troubleshoot that now. The point is that for the blue filter, it gave me 2 real poles at exactly the same frequency. Whereas in the red filter, look what I got. I've got 2 imaginary poles, okay, and their locations have been picked by the computer. Okay, I told the computer like some stuff, and the computer is the one that calculated where those poles should be in order to give me the filter that you're seeing. And that's what we're going to learn today, is like how to tell the computer what you want so that the computer can just pick the poles for you. Because that's sort of the hard part, right? Once you know where the poles are, then you can you can just go build a circuit to actually implement those poles, and we can learn how to do that if you're interested. Okay, so far all I want you to take away from this is that I've got 2 systems. Each one has 2 poles. One of them had 2 real poles. One of them had a pair of imaginary poles. And yet, even though in terms of complexity they're exactly the same, one of them is a much better filter than the other. Now, let me rerun this. Okay, let's ditch the purple signal for a second. Okay, now let's compare. Now let's add the green signal to the mix. So we're done with the blue signal, right? The blue filter is a loser, right? There's nothing preferable about the blue one. Like if you show me the blue one, I'll say use the red one. Okay, it wins. There's nothing better about the blue one than the red one. But now let's compare the red one and the green one. Which is a better filter? What was that? Depends.
The green cuts off better, and if you're really looking for the frequency at the cutoff frequency, it will pass that perfectly fine. If you want to pass the band in front of it, it's going to be a little bit less than red though.
Interesting. So look at this. Here you're making a deal, right? Everything in engineering is a trade-off. So here you're making one of these classic engineering trade-offs. All right? So again, this is still, the green filter is still a two-pole filter. It's just as complicated as the red filter in terms of physically how you build it. But look at the trade-off that you've made. You're essentially saying, I want better performance in the stop band for my two poles. Am I getting better performance in the stop band? You bet. Okay, again, pick a frequency, 1,000 hertz. The green signal is getting me about negative 45 dB. The red signal is getting me about 40 dB. So that's a difference of about, again, 5 or 6 dB. That's another factor of 2. So the green one is about double the rejection of the red one. Okay. Now, what price did we have to pay for that? Well, the price we had to pay was we had to be willing to tolerate a little slop in the passband. All right. So one way of defining the passband is to say, well, I want you to be as flat as possible, okay, until the cutoff frequency, and that's what the red signal is. But another way of saying it is, you know, I have this 3 dB number, okay, and what I'm basically saying is, as long as within the passband you're passing the signal at 3 dB or better, I'm not real picky, okay? If you want to dip down a little bit at some frequencies and you know, up at other frequencies, I don't really care as long as you're passing the signal with at least 3 dB. Okay? And that's what you're getting in this case, right? The green signal does this thing where it dips and it comes back up. So some of your passband frequencies are getting multiplied by 0.707, so they're getting reduced a little bit. And some of your passband frequencies are getting rejected perfectly, like at about maybe 100 or you know, maybe like 70 or 80 hertz. They're getting passed perfectly. So you have some difference in how your passband frequencies are being passed. Now, is that ideal? No. Okay, it's not. But it's a trade-off. If you can tolerate that in your application, then in exchange for being willing to tolerate that, you get awesome stop band performance. Okay, you get much better stop band performance for a filter that's exactly no more complicated. It's still a two-pole filter, right? Meaning that it's exactly the same circuit. You would just change some, like a resistor value, basically. Isn't that cool? I mean, that's a neat trade-off to make. So it sort of depends on your application, right? Some applications, you may really value for a really high premium on saying, I need all my pass frequencies to pass perfectly. Okay? Well, then you'd use a Butterworth filter. All right? And if you need better rejection, then you have to use a Butterworth filter, but instead of a two-pole filter, maybe you do a three-pole filter or a four-pole filter. So you have to build a more complicated circuit. Or maybe your application, it doesn't really matter as much. Okay? Then you say, well, I think I can do the Chebyshev filter, and I can get away with a two-pole filter instead of having to build a four-pole one. So I save money. Right? Because I don't have to buy as many parts. So my printed circuit board can be smaller. Right? The manufacturing time is less because there's less things to solder. So all those are bonuses. All right? Now we have the last one. Oh, and again, to compare the red one and the green one, again, it's just a pair of complex conjugate poles. It's just the poles are at different frequencies. All right? And then we can play this game one more time to create what's called the elliptic filter. And the elliptic filter is really bananas. The elliptic filter basically says you actually can't see much of a difference with the elliptic filter now. So the elliptic filter, the way it works is it says, you say, for the pass band I need at least 3 decibels. For the stop band, you only need to reject up to 40 dB. Okay, so it's sort of, it's not that great in the stop band. But the advantage is it's great in the transition band, right? It's sort of outperforming everything in the transition band in exchange for not really caring what happens deep into the stop band. But again, that may be a deal you're willing to live with. I mean, rejecting something with negative 40 dB, that's dividing it by 100. That's pretty good, right? You might not need to reject your signal by any more than that. So it's all kind of application dependent. So how do you know which one you need? You sort of go trial and error, right? You get some sample data and you try filtering your signal. What does it look like when I filter with a Butterworth or a Chebyshev or an elliptic filter? You mess around with it and you see what happens. Oh, okay. You know, I tried filtering some sample data with the elliptic filter and it looked great. I think I can do that. Or it looked like crap. I can't use it. Okay, so that's kind of what guides you. So just real quick, I want to play this game now. I'm going to increase the, just so you can see how this works. These effects are sort of more pronounced if I increase the filter order. So here's a second order filter, third order filter, fourth, fifth, and so on. Okay, so again, if you look at the fifth order filter, I mean, some of this stuff's getting pretty interesting, right? Like, if you look at the fifth order filter, look what's happening. The Butterworth filter basically gave you a bunch of poles on a circle. The elliptic filter basically gave you a bunch of poles on an ellipse. And the that was the Chebyshev. And the elliptic filter gave you a bunch of poles and a bunch of zeros. Okay, so that one's even more sophisticated to build. All right, what do you think of the purple filter? Is it any good? Depends. That's the whole point. It depends, right? It's, you know, your stop band is kind of all over the place, but who cares? Like, you've already negative 40 dB. You've already divided your signal by at least 100. That's pretty good, right? But look at, you're getting, in exchange for that, you're getting a really nice transition, right? It's cutting off way faster than the green or the red one. So it really depends on your application. So this is how we design filters, okay? You basically pick from one of these families of filters. Butterworth, Chebyshev, and Elliptic. Those are the main families. There are other families, okay? Some engineer once upon a time sat down and decided this is like this Butterworth filter has these properties and it's good for these reasons. And there's basically a bunch of equations that say if you want a Butterworth filter that cuts off at this frequency with this many poles, then put the poles at these locations. Okay, and ditto for the other kinds of filters.
This is only for analog filter design?
Right. Right now we're just talking about analog filters. Okay, we can talk about digital filters. It's a different beast. All right. So all you need to know to build these, it's actually not that hard. Right. So look at the code that I need to do this. And I'm posting this code so you can just play with it for your computer assignment. Suppose I want to make a Butterworth filter. I say there's a built-in function called butter. Okay? Build me a Butterworth filter with n poles, where n equals 5, with this cutoff frequency, right? 2 pi times 100 radians per second. And I want, you have to put the S flag. The S flag says I want an analog filter. Okay? And lo and behold, it builds you an analog filter. Okay? H butter becomes your transfer function. Okay, so if I actually want to see what that looks like, I can say H butter. Oops, it's capital H butter. There's my transfer function. What if I actually want to simulate my analog filter on some data? What function do I use for that? LSIM. LSIM is the thing we learned on Friday. Okay, LSIM will do an analog simulation. Okay, we'll simulate an analog filter on your data. And then you can see the result. If you want to see the step response, you say step H butter. I don't know, is that going to look like anything? There you go. There's your step response. Okay, and you can play this game all day. What if you want to build a bandpass filter or a high pass filter? Like maybe you might need that for your homework. Doc butter. Doc is like a MATLAB word that means documentation. So pull up the documentation for the butter function. Okay, let's scroll down here. All right, so it looks like if I give it the F-type flag, I can make a high filter or a low filter or a stop band filter. Okay, so for example, I can come here. I can say numerator, denominator equals butter, 5 poles, 2 pi, 100. Wait, was it frequency first or? I already forgot. I suck. Oh, it's cutoff frequency and then type. Stop band analog filter. Must be, not stop, I wanted a high pass filter. Okay. H equals TF numerator denominator, ODH. And look at that. What do I got? High pass Butterworth filter with a cutoff frequency. Oh, it gave me my cutoff frequency. It plotted the axis in radians per second. If I right click, I think there's a way to twist its arm. Properties. I'd like my frequencies in hertz. Kilohertz? Look at me living the dream. Okay, let's put a grid on there. And I've just built myself a high pass filter. Where am I? Grid. Okay? Now, again, I'm free to put my poles wherever I want. I'm not obliged to use a Chebyshev or a Butterworth or whatever worth. Okay? It just happens that those filters are common filters. They're very clean. They have certain nice properties that are well understood. You can stick your poles wherever you want, right? You can daisy chain real poles together all day. Okay? And to some extent, there's really not that much wrong with that. But this is sort of like a more common way of doing it, is to limit yourself to these families of filters with these well-known properties. You go to your engineering tool, whether it's MATLAB or something else. You say, I want poles. I want them at these frequencies. Boom. It designs the system for you. Okay? Then if you actually want to build it, then there's an extra step where you actually, if you're doing it with a circuit, you can actually build a circuit that can locate the poles exactly where you want. Okay, and that's yet another step which we can discuss on, I guess we can discuss that on Wednesday if you're so inclined. All right? But I definitely wanted to get this out here for today. I want you to download this code and look at it. You've got examples. This is building the Chebyshev filter, the elliptic filter. You should experiment with high-pass filters, stop-band filters, because those will be basically the tools that you want for your computer assignment. I don't think I put this in the computer assignment, but I would like everybody to use the lsim command to simulate their filters. There are other ways of doing them, but those are digital filters, and sometimes those lines get blurred a little bit. I want everyone to stick with the analog filtering techniques, okay? Yes?
I just had a question. I noticed you use like the num and denom.
Yes.
For num, you define, or no, denominator, the poly poles, the poly function.
Yeah.
What is that?
Okay, so here's my denominator. So it's basically like constant plus this number times s plus this number times s squared, s cubed, s to the fourth, s to the fifth.
Okay.
So what I can do is, if I want to see where my poles are, I can say, let's say r equals roots of denominator. And it will give me the roots. It will factor that polynomial. So those are where the roots of the polynomial are. You know, if you looked at the pole zero diagram, there's your poles. The poly function is the backwards of this. The poly function says, if you say, hey, give me a polynomial with those roots, it'll spit the polynomial back at you. Which is a handy thing to know. Okay, sorry I was late. I'll be on time on Wednesday. I don't have to drop anyone off at school tomorrow on Wednesday, so I should be good.